kinetic frictional force, or F sub F sub K. Specific learning outcome: solve problems involving kinetic friction. For the motivating or prompting questions, in which of the following situations is kinetic friction present? Number 1, an apple is at rest on a table. Since this apple is at rest on a table and it is not moving, then kinetic friction is not present. Number 2, a car speeds up on a road. Since this car is moving, then kinetic friction is present. Number 3, a man pushes a cabinet. The cabinet doesn't move. Because a cabinet is at rest, then there is no kinetic friction. Number 4, a block of wood sliding on an incline. Since the wood is moving, then there is kinetic friction. Number 5, a dog is running on a pavement. Since a dog is moving, then there is kinetic friction. In equation form, kinetic friction or kinetic frictional force F sub K is expressed as F sub K equals mu K F sub N, where mu sub K is a coefficient of kinetic friction and F sub N is the normal force. So unlike static friction, our kinetic friction has only one value. Table 4.2 lists some approximates of coefficient of kinetic friction between two materials or surfaces in contact with each other. For glass on glass, approximate value is 0.4. Rubber on dry concrete, approximate value of coefficient of kinetic friction mu sub K is 0.8. Steel on steel, 0.57, aluminum on steel, 0.47, and wood on wood, 0.20. Comparing the coefficient of static friction and kinetic friction in tables 4.1, the previous table, and 4.2, it can be deduced that between two materials in contact, the coefficient of kinetic friction is less than the coefficient of static friction. Also, this is because the interlocking of molecules between the surface and object has already been broken loose the moment the object moves. Furthermore, given the values of the coefficient of static and kinetic friction, coupled with equations 4.1 and 4.4, it can be concluded that for an object and its surface of contact, kinetic friction is less than static friction. Thus, it is easier to maintain the speed of an object than to make it initially move. To show, let us discuss another example, sample problem 4.2, which is just a continuation of sample problem 4.1 or the previous problem. Sample problem 4.1, you can keep the refrigerator moving at constant speed with a pushing force of 350 newtons. Find the kinetic friction F sub K and coefficient of kinetic friction mu sub K between the refrigerator and floor. We have here the free body diagram. This object now moves to the left at constant speed, so not accelerating. Applied force to the left, and then we have now the opposing force F sub K to the right. Normal force is perpendicular to the surface, Fn, and of course Fg or weight is downward. So for the summation of Fx, Again, we have minus x, negative sign to the left, and plus x to the right. And up is plus y, down is minus y. So summation of fx, sum of all forces along x, we have negative fa plus Fk, kinetic frictional force, equals, since the object is moving but not accelerating because it is moving at constant speed along a straight line, equals 0 and not ma. And then summation of Fy is equal to, going up, we have a force there, Fn, normal force. Going down, you have Fg, so minus Fg, equals, along the y-axis, there is no movement, so equals 0. We are now to solve for the kinetic frictional force. So let's call that letter A, solving for the kinetic frictional force, Fk. Looking now at our two equations, we can see that we can use summation of fx. So we have minus fa plus fk equals 0. You want this f of k, so we transfer negative fa to the right side of the equation, leaving f of k on the left side and positive fa. In the problem, the applied force is the constant pushing force. Applied force is 350 newtons. It's given. So that's the answer, 350 newtons. So that's also the FFK. Next is letter B, solving for mu sub k. Solving for the coefficient of kinetic friction, mu sub k. We have the equation 4.4 f sub k equals mu k fn. We want the mu k, so we divide the entire equation by fn. Divide by fn both sides of the equation. So fn over fn, that's 1. So leaving us with ffk over fn, the right side, and equals to mu k. ffk, we have solved this one, our answer earlier, which is 350 newtons, but we have no fn. So we look at our equation now, and we can see here in our summation of fy that we have here the fn variable. Fn minus Fg equals 0. So we are going to use this one. Fn minus Fg from summation of Fy. We have Fn minus Fg equals 0. We want the Fn, so Fn is equal to, this goes to the right side, Fg. But what is Fg? We know that but Fg is just the weight, and weight is mg. So the mass of our appliance, as given in the previous problem, is 75 kilograms times g is 9.8 meters per second squared. Again, for the g, we will use positive when we solve for weight because the signs for the g is already taken care of during the formulation of the free body diagram equations, summation of Fy. Okay, so 75 times 9.8, the weight is 735 newtons. So this is the weight, which is Fg, newtons, which is Fg, and Fg is equal to Fn. Fg is 735 newtons, so Fn is also 735 newtons because Fn is equal to Fg. Now use this one in our equation here in the left side to solve for mu k. So we have solved for Fn already. Let me drag this one up. The FFK that we have obtained was 350 newtons. In letter A, 350 newtons. Over this one, Fn is 735 newtons. This is our coefficient of kinetic friction, mu sub k, newtons over newtons, that cancels, so leaving us with 350 divided by 735. Using your calculator, you should get 0.48 as the mu sub k. Thank you for watching.